Friends, oil gases talk about temperature and energy. But carbon monoxide talks about life. When CO rises in a DGA report, it is not the oil that is speaking, it is the paper insulation. And paper insulation means winding health, mechanical strength, and remaining transformer life. Many engineers focus only on hydrocarbons and completely miss this silent message. But senior engineers know one truth. CO is not a fault gas. CO is an aging gas. In today's Electroverse episode, we decode carbon monoxide, CO, in Transformer DGA. Why CO is generated from cellulose paper. How thermal stress breaks down insulation. Difference between CO and hydrocarbon gases. How CO trend predicts loss of mechanical strength. When CO is acceptable. And when CO signals irreversible insulation damage. Stay till the end, because CO tells you not how the transformer is running, but how long it will survive.
When we talk about dissolved gas analysis in power transformers, most engineers focus on the usual suspects: hydrogen, methane, acetylene. But there's one gas that's even more critical, and it tells a completely different story. We are no longer talking about oil alone. Today, we're talking about paper insulation health. And the key gas here is carbon monoxide. Carbon monoxide in DGA isn't just another fault gas. It's fundamentally different from all the others because it comes from cellulose decomposition, the kraft paper and pressboard that forms the backbone of your transformer's insulation system. While other gases warn you about oil degradation or electrical faults, carbon monoxide warns you about something far more serious: the slow, silent consumption of your transformer's insulation life. According to IEC 6599 and IEEE C57.104, carbon monoxide is generated mainly due to thermal degradation of paper insulation, moisture-related aging, and long-term overheating of solid insulation. Think of it as a silent aging indicator. It forms due to natural aging processes, elevated temperatures, moisture ingress or oxidation, even when there are no visible electrical faults happening inside your transformer. The standard limits for carbon monoxide are quite specific. For normal conditions, you want to see carbon monoxide below 400 ppm. When it's between 400 and 600 ppm, you're in the caution zone. This is where you need to start paying attention. Above 600 ppm indicates abnormal conditions that require immediate engineering action. But here's where many engineers make mistakes. They look at a single carbon monoxide reading and try to make decisions based on that number alone. The trend of carbon monoxide over time is far more important than any single ppm value. A stable, moderately high carbon monoxide level in an older transformer might just indicate normal aging. But a steadily increasing carbon monoxide trend, that's telling you about accelerated paper degradation or thermal stress that needs your attention. Let me walk you through the different scenarios you'll encounter. In the first case, you see stable carbon monoxide levels that are moderately elevated but not increasing significantly over time. This typically suggests normal aging, especially in transformers that have been in service for many years. The paper insulation is aging naturally, and the carbon monoxide generation has reached a steady state. In the second case, you notice carbon monoxide levels that are steadily increasing over consecutive DGA samples. This indicates accelerated paper aging or thermal stress on the insulation. The rate of increase tells you how quickly the insulation is being consumed. If you're saying increases of more than 30 ppm per month, you need to take action quickly. The third case is the most critical. Carbon monoxide rises sharply together with ethylene or acetylene. This combination indicates active thermal or electrical damage to the paper insulation. This is a high-risk condition that demands immediate investigation and possible removal from service. When you encounter elevated carbon monoxide levels, your engineering response should be systematic. First, review the transformer's loading history. Has it been operating at higher than normal loads? Check the moisture content in the oil, because moisture accelerates cellulose degradation significantly. Increase your DGA monitoring frequency to track the rate of change more closely. And most importantly, start planning for insulation life assessment studies.
Carbon monoxide should never be analyzed in isolation. You must interpret it alongside carbon dioxide levels, calculate the carbon dioxide to carbon monoxide ratio, and consider the transformer's age and operating temperature history. The carbon dioxide to carbon monoxide ratio is particularly telling. A ratio below 7 indicates potential problems, while a ratio below 3 with elevated furans suggests severe and rapid cellulose degradation. Here's the key insight that separates experienced engineers from novices. Carbon monoxide does not demand panic. It demands planning. Fault gases like hydrogen or acetylene warn you about events that are happening right now. Carbon monoxide warns you about life consumption that has been happening over time. It's telling you that your transformer's insulation is being consumed and you need to plan accordingly. The beauty of understanding carbon monoxide trends is that it gives you time to act. Unlike sudden electrical faults that can cause immediate failures, insulation aging is a gradual process. When you see increasing carbon monoxide trends, you can plan maintenance windows, prepare for insulation assessments, and make informed decisions about the transformer's remaining life. Ignoring carbon monoxide means you are blind to insulation aging. You might have a transformer that appears electrically healthy based on other fault gases, but is actually approaching the end of its insulation life. This is why carbon monoxide monitoring is so crucial for asset management and long-term planning. The relationship between carbon monoxide and furans provides even deeper insights into insulation condition. When carbon monoxide levels are elevated and increasing, furan analysis becomes essential. Furans are the chemical fingerprints of cellulose degradation. Normal transformers show furan levels below 100 parts per billion. Levels between 500 and 1000 ppb indicate accelerated aging, while levels above 1500 ppb suggest high risk of insulation failure. Temperature plays a crucial role in carbon monoxide generation. Even a 10-degree increase in operating temperature can significantly accelerate the rate of cellulose degradation and carbon monoxide production. This is why understanding the transformer's thermal history is so important when interpreting carbon monoxide trends. Moisture is another critical factor. Water in the insulation system acts as a catalyst for cellulose degradation, dramatically increasing carbon monoxide production. A transformer with high moisture content will show elevated carbon monoxide levels even at normal operating temperatures. This is why moisture control through proper maintenance and monitoring is so important. The engineering actions you take based on carbon monoxide trends can significantly extend transformer life. When you see increasing trends, consider load management to reduce thermal stress. Implement more frequent oil processing to remove moisture and oxidation products. Plan for insulation drying if moisture levels are high. And most importantly, use the carbon monoxide data to make informed decisions about transformer replacement timing. Remember, transformers don't fail suddenly. They age silently. Carbon monoxide is your window into this silent aging process. It tells you not just that aging is happening, but how fast it is happening and whether your current operating practices are accelerating or managing that aging effectively. The key to successful carbon monoxide interpretation is understanding that it's not about the absolute value. It's about the trend, the rate of change, and the correlation with other indicators like carbon dioxide, furans, and operating conditions. When you master this understanding, you transform from someone who reacts to transformer failures into someone who prevents them through intelligent asset management. This is why carbon monoxide analysis is so powerful. It shifts your perspective from fault detection to life management. Instead of waiting for problems to occur, you're actively monitoring and managing the consumption of your transformer's most critical asset, its insulation system. And that's the difference between good engineering and great engineering.
So friends, this is the real meaning of carbon monoxide in DGA. CO does not indicate arcing. CEO does not indicate oil cracking. CEO indicates paper insulation degradation. It tells you cellulose is breaking down. Thermal stress is affecting windings. And insulation. Life is being consumed. Remember this rule forever. Hydrocarbons. Fault energy. Carbon monoxide. Insulation health. When CO rises slowly, you monitor and manage loading. When CO rises rapidly, you investigate immediately, because paper damage cannot be reversed. If this explanation helped you read DGA like a condition monitoring expert, then support. Electroverse. Like this video, it helps serious engineering content reach more professionals. Comment below. Have you seen CO increase without hydrocarbon rise? Subscribe, because this channel explains transformer life, not just alarms. In the next episode, we decode carbon dioxide, CO2, and learn how CO2 ratio reveals insulation aging severity. You've been watching Electroverse, where every spark tells a story. Stay charged, stay safe, and happy.